Let's pump out a few video solutions to problems in Chapter 3. This is, of course, from Randall Knight's Physics for Scientists and Engineers, A Strategic Approach with Modern Physics, 4th edition. That's a mouthful. And the first problem I'll take a look at is number 8 from this chapter. Here's number 8 from the Pearson e-text. Not downloadable. Got to have your subscription. They give us two vectors named C and D, and you'll notice they've got the parentheses with an ordered pair of descriptors, but these are actually not Cartesian components. They tell us instead the length of the vector and the angle that it makes. So these are really polar components, but they're not the conventional polar components, because if you'll notice here, they tell us that vector C makes an angle of 15 degrees with the negative x-axis. So we already know that we're not measuring angles with respect to the positive x-axis necessarily. I'm looking for the pause button here. We'll begin with vector C. This is the information that we have, so I will draw that picture. 15 degrees above the negative x-axis. Now, I think the angle that I drew here was bigger than 15, but this makes it easier to visualize. First off, this 15 degrees is not measured with respect to the positive x-axis. So we can't use those standard formulas that I presented in a previous video. We're going to have to go back to our trig functions. It's like I keep saying, you don't want to focus too much on memorization or which procedures to use. Focus on understanding. If you really understand the trig functions and how to use them, you'll be flexible in your problem-solving skills. I am going to give this angle a label different from theta. I try to reserve the letter theta for that standard angle measured, or conventional angle measured from the positive x-axis. So in this case, I'll call that angle phi, and all I have to do is use my knowledge of trig functions. I know the length of the hypotenuse because that's given, and the y-coordinate, for instance, would be the opposite side of that triangle. So I take the hypotenuse, I multiply by the sine of phi. That's what this formula right here says. And I'm giving it a plus sign because I know that this y component points in the positive y direction. The x component, however, does point along the negative x-axis. So first I will use the trig functions just to get the length of this side, and then I will insert the minus sign. So the adjacent side here should be the hypotenuse times the cosine of phi. That gives me the length, and then it's up to me to insert the minus sign because I'm observing that the x component points in the negative direction. Now you may be thinking, wait a minute, doesn't the cosine function maybe take care of that for us? No, not in this instance, because we're using this angle, not the conventional angle. In fact, anytime you use a triangle like this where all of the angles are less than 90, except for, of course, the right angle over here, but both of these angles are less than 90, which means those angles are in quadrant 1. Don't be confused about the difference between the vector here, which clearly points into quadrant 2, and the angles within the vector. Those angles are quadrant 1 angles because they're less than 90. And both cosine and sine take on positive values in the first quadrant. So it's up to you to insert the minus sign. Now I plug in numbers, and I get these two values for the x and y components. As we hoped, the x component, or as required, the x component is a negative number. And we can see that the magnitude of the x component, which is close to 3, is considerably greater than the magnitude of the y component. Makes sense when you look at the picture, right? This side is more than 3 times longer than this side. Not as I drew it, but it's supposed to be. Could we do this with the regular formulas? Well, if you'd like to use the typical formulas, which is a safe choice because it will always work, you first need to determine the angle that vector C makes with the positive x-axis. That would have to be 165, the supplement of 15. Now that we know that angle, we can just plug and chug. So we go back over here to our regular old formulas. You can always find the x component by taking the magnitude of the vector and multiplying by the cosine of the angle that the vector makes with the x-axis. See the difference in these formulas here? Over here I've got a minus sign, here no minus sign. Same thing for y. You can always just multiply the length of the vector by the sine of the angle that the vector makes with the positive x-axis. Now, in this case, there's a sine function for c sub y, and over here we also used a sine function. It's not always like that. Sometimes you might actually be using a cosine here versus a sine, depending on which angle you labeled. So again, you want to be flexible with your use of the trig functions. What about vector d? We're told that that vector is quite a bit longer. Now, I think the previous vector was around 3 meters, right? This one's 25. I can't actually draw a vector that's proportionally longer because it wouldn't fit on the screen. The angle that it makes is 30 degrees to the right of the negative y-axis. So that's why I've swung d to the right here. Again, this is not the conventional angle. We have not specified the angle with respect to the positive x-axis. So it's going to be up to me to make that correction. Now, for this vector, the x component is clearly positive. It points along the positive x-axis, and the y component is negative. We need to take that into account if we're going to calculate the components using this, what you might call a reference angle. So again, I will label that angle phi. You don't have to, but I don't want to call it theta. I like to reserve the letter theta for the conventional angle. In this triangle, the x component is the opposite side of the triangle. So I'm going to use the sine function. I take the hypotenuse of 25.6. I multiply by the sine of what I'm calling phi. And notice I've plopped a plus sign in front because the x component is positive. On the other hand, the y component, which does point downwards, needs a minus sign in front. Because if I use the cosine function to find the length of the adjacent side, that's going to spit out a positive number. Hypotenuse times the cosine of 30 would actually be a positive number. It's up to me to insert the minus sign since I know that the y component is negative. Plug in numbers, and I get these values. Y component is negative as required. The x component is positive. Let's check this using the conventional formulas. We need to know the angle that this vector makes with the positive x-axis. Well, you'll notice that the vector is swept out clockwise, which is a negative angle. So if this is 30 degrees, we know 90 minus 30 would have to be an angle of 60, specifically negative 60. Now that I know theta d, the angle that vector d makes with the positive x-axis, I can go ahead and use the regular old formulas where dx is d cos theta d and dy uses the sine function. And of course, we get the same answer. It's up to you which you prefer. I don't really have a preference. It works either way. Sometimes it's easier to do this so that you don't have to think about what this angle is. It really doesn't matter. As long as you're familiar with your trig functions and that you've got these formulas, you should probably memorize these formulas. And here's an instance where, check it out, the first way that I did it, in order to calculate the y component, I used a cosine function. And then with the standard way, you would use a sine function. So don't be confused by that. The reason why we went from a cosine to a sine is because of the triangle. It's because of the reference angle that we used. Just know your trig functions, know how to use them. Is that it for this problem? Okay. Next up is number 18 from chapter 3. Different type of problem. They specify a vector 5 meters long, and it's 30 degrees counterclockwise. That's this direction. 30 degrees counterclockwise from the vertical, which would be this direction. And what they're asking you to do is to resolve that vector into components along two different sets of axes. We've got two different coordinate systems here. In each case, the axes are orthogonal, so it's still an orthogonal coordinate system, but these axes are rotated by 30 degrees or tilted with respect to these two. And this is a good exercise because it's not always the best choice to have your y-axis be vertical and your x-axis be horizontal. We will be doing many problems having to do with things sliding up or down a ramp, and in most of those problems it's actually more beneficial to rotate your axes. So don't get too attached to vertical and horizontal. Where does that word vertical come from anyway? Like horizontal makes sense because it's in the direction of the horizon, but what's with that word vertical? I don't know. Let's start with the initial, or the first set of axes, and I've drawn the vector as they described it. It's tilted 30 degrees counterclockwise from the vertical. And since we've had some practice with this now, I think I'll skip a couple steps. Let's go straight to using trig functions on this triangle to get the components. We know that the x component needs to be negative, it points to the left, and the y component needs to be positive because it points along the positive y-axis. For the x component, this component right here, that side is opposite the angle 30, so we'll go with, oh, there's my labels, we'll go with hypotenuse of 5 times the sine of 30 to get the opposite side. I've inserted the minus sign because I know that the x component needs to be negative. The y component is the adjacent side of this triangle, so I will go with hypotenuse times the cosine of 30. I leave it positive because, again, the y component points along the positive y-axis. This should work just fine, but you'll notice these are not the conventional formulas. Conventionally, you would say bx is b cos theta b, where theta b is the angle between the vector and the positive x-axis. So since we're using a different angle, this is not the conventional angle, we would have to use different formulas. But we can check that these results are the same as the results that we get from these standard formulas. Oops, this should say theta b. I'm not going to fix that. This should really say theta sub b. Remember, this is a right angle, so 90 plus 30 tells us that the angle that vector b makes with the x-axis would actually be 120 degrees. And now that we know that angle, we can plug it into our conventional formulas. So b sub x should be the magnitude of b times the cosine of the angle that vector b makes with the positive x-axis. We get the same number that we got previously. The y component can always be found as the length of the vector times the sine of the angle that the vector makes with the positive x-axis. Same number. And as expected, the y component comes out positive, x is negative, and the y component is the longer one, which is why this number is greater in absolute value than that number. Now let's repeat this procedure for the rotated axes. So watch the magic here. Here's the xy axes. Here's the new xy axes. I'm going to go back and forth there. See how the vector is not changing. It's the coordinate system that we're changing. We're tilting it. Now, in many books, it's customary to indicate that these are different axes by putting a prime next to the x and the y. So I will call these the x prime and y prime axes to distinguish them from the original axes. And they chose the 30-degree tilt here to make this problem a little easier. Remember, vector b is tilted by 30 degrees from the vertical. So that's why the new y-axis, the y prime axis, lines up with the vector. And that will make it very easy to determine the components in this new coordinate system. Just kind of tilt your head if you need to and look here. Tilt your head by about 30 degrees. Do you see how the vector b has no component along this axis? How do I know that? It's because vector b is actually perpendicular or orthogonal to the x prime axis. Any vector that's perpendicular to an axis has no component or has a component of 0 along that axis. That's a very important fact that you should memorize. And since the vector b is parallel to the y-axis, or I should say the y prime axis, then the y prime component is the full magnitude of vector b. And again, notice how I left off the arrow symbol here. I just wrote b, so I'm really referring to the magnitude of b. And I suppressed the units. I just wrote 5. It's really 5 meters. Okay, so just by inspection, as they say, we can see that the primed, or the x primed component of vector b is 0, and the y prime component is the full 5 meters. Now, if this vector had been pointing in the opposite direction, so it was still parallel to the y-axis, y prime axis, but in the opposite direction, then you would just stick a minus sign in front. Can we check these results with our formulas? Well, remember, if you want to use the conventional formulas, you need to know the conventional angle. What's the angle that our vector b makes with the x prime axis now? That's a 90-degree angle. So we can plug that into our conventional formulas. You can always find the x component of a vector by taking the length of the vector times the cosine of the angle that the vector makes with the positive x-axis, in this case the positive x prime axis. And remember that the cosine of 90 is 0. You should remember that. That's a little fact that you should have in the front of your brain. Cosine of 90 is 0. The sine of 90 is 1. So yeah, we get the same numbers. These formulas will always work provided that you are using what I'm calling the conventional angle. One last point I'd like to make about this problem. Here are what I'll call the unprimed components, and here are the primed components of the vector B. Two different sets of numbers, right? Is there perhaps a more direct way of relating the primed components to the unprimed components? Rather than looking at both pictures and using trigonometry, is there some process by which you could turn the unprimed components into the primed components for any vector? It turns out there is. It's called a rotation matrix. You don't need to know any of this stuff. We're not going to use this in this class, but you'll likely see it in a future class. It turns out that for a given rotation, see, we've got our x and y axes that have been rotated through an angle theta. There's a 2x2 matrix that you can use, and you multiply that rotation matrix by your initial coordinates, those are these, and out will come the primed coordinates, or primed components. So it's more methodical. And those rotation matrices, typo here, rotation matrix, that's the sort of thing I would do when I'm preparing slides. So these rotation matrices have some interesting properties that you may learn about in linear algebra. This next problem from chapter 23 gives us an opportunity to use our new understanding of how to take the derivative of a vector. So we're told in this problem that some particle moves according to the following function of time. Its position at any time is given by, and they first express it in terms of the basis vectors, 5 units in the I hat direction plus 4 units in the j hat direction. All of that times the square of the time. And then they add the units here, m for meters. So we can already see that the position depends quadratically on the time. And what they'd like to know is, how far is the particle from the origin at a number of times? What is the particle's distance from the origin? Well, remember, for any position vector r, the distance is just the length of the vector. So we really need to find the magnitude of this vector, which amounts to converting from rectangular coordinates to what you might call polar coordinates. The length of a vector could be considered like a polar component of that vector. And for that, we can always use Pythagorean theorem. So here's one way to do it. In this book, and many books in physics actually, the letter r means the magnitude of the vector r. Now, if I want to be clear, I could say that's defined as the magnitude of the vector r, where I've put vector r enclosed in the absolute value signs. Some math books would even do the double line, which is called the norm. Different notations to mean the same thing. We'll just go with this. And this would be the square root of, now I could put r sub x squared plus r sub y squared, because that's what you would do for any vector. You take its x component and its y component, you square them, add them up, take the square root. But we actually have a special name for the x component of the position vector. We just call it x. So what we're really doing is taking x and squaring it, y and squaring it, adding it up, taking the square root. But don't forget that each of these quantities depends on time. So let me rewrite this a couple ways. The position vector is a function of time. I could distribute the t inside the parentheses, so this would really be 5t squared in the I hat direction plus 4t squared in the j hat direction. But remember how it's not really necessary to write these basis vectors. It's kind of implied if we just write an ordered pair of the components. So this is, and I'm going to abbreviate 5.0 now, it's just 5. This is really 5t squared, comma, 4t squared. It's understood. This is the component along the I hat direction, component along the j hat direction. And once again, you could even pull the t squared out and write it like this, 5 comma 4 t squared. So this is the same as that, which is the same as this, which is the same as that. You want to be flexible. So the absolute value, let me put r without the vector symbol as a function of time. This means the distance which is the length of r, as a function of time. That would be the square root of 5t squared squared. Be careful, we're squaring 5t squared plus 4t squared squared. Now, do you recognize that both of these terms have a t squared in common? So I'm going to factor the t squared out of these two and write this as t squared. It's actually a t squared squared that they both have in common. And this would be 5 squared plus 4 squared. See what I've done? Both of these have a factor of t squared squared in common, and I factored it out. And you know the rule. The square root of ab, at least for real numbers, for positive real numbers, is root a, root b. That's how the square root function works for positive numbers, and 0. So let's pull out the square root of t squared squared. What is the square root of t squared squared? That would just be t squared. Root 5 squared plus 4 squared. It's easy to get, or to lose track of how many times we're squaring things here. So this is 25 plus 16. What is that? 25, so 35, 41. Taking the square root of 41, that's not a perfect square. 25 plus 16 equals square root I'll keep a few digits for now. Oh, yeah, 6.40 t squared. Okay. Now, this kind of looks familiar, doesn't it? This reminds me of how your displacement in one-dimensional motion for constant acceleration, your displacement looks like this. 1/2 a delta t squared. You've got that quadratic dependence on time. In fact, if you start from rest so that your initial velocity is 0, these equations are practically identical. This one says your displacement from the origin is a constant times the square of how long you've been moving, and we've got the same equation here. Now, this equation is valid for constant acceleration. So, if our position, or if our distance from the origin in time obeys the same force law, or not force law, excuse me, the same formula, I'll put it, as this constant acceleration kinematic equation, then perhaps this is indicative of constant acceleration motion. And in fact, we haven't really talked yet about getting the acceleration vector from the position vector, but you'll find that if you take the derivative of the position vector twice, once gives you velocity, the next derivative gives you acceleration, you will end up with a constant vector. In fact, I think I'll show that in a moment. But now that we've got our formula for distance as a function of time, let's evaluate that for a few times. They'd like us to calculate this, the distance from the origin at 3 different times. What are those 3 times? T equals 0, 2, and 5 seconds. Find the distance from the origin at t equals 0, 2, 5 seconds. Let's just do one of them. That should be sufficient. So the distance from the origin, notice I'm not drawing the arrow because I'm not talking about the vector r, I'm talking about the magnitude of r, which is the distance from the origin. The distance evaluated at t equals 2 seconds equals, now this is a little overkill with the notation. I could have just put r parentheses 2 and it would be understood it's the distance at 2 seconds, but this is extra clear. That would be, we take 6.40 and we multiply it by 2 squared. Notice I wouldn't want to plug in 2 seconds squared because then my units would come out seconds squared, which is definitely not the units of distance. So what's going on here is this constant out front really contains some dimension that I didn't write down. You could go back to the equation and figure out what those units are, but right now it's probably safer just to suppress the units altogether. This is 4 times 6.4. So at the end I'll go ahead and add the meter symbol. This is how far we are from the origin. Okay, so you could have done this the following way. You could have gone all the way back to the vector expression for the position at any time and plugged in the various times, 0 seconds, 2 seconds, 5 seconds, you could have plugged in the time for those 3 separate times, and then for those 3 separate vectors, use Pythagorean theorem to find the magnitude of the position vector at that time. But that's unnecessarily, well, that's inefficient, right? Because we can just find the function for distance once using Pythagorean theorem. This is now just a scalar, and now we can merely plug in 3 different times. And there's one of them. What's another way to do this? Well, I like doing it this way. You'll notice that the position at any time is this constant vector times the square of the time. So let's introduce, or let, the vector capital R. I'm just defining a vector for the purposes of this problem. And it's the vector 5, 4, where it's understood these are Cartesian components. That's this vector right here. Then we can write that the position vector at any time is just big R times t squared. It's a constant vector times the square of the time. This is just a short way of writing this. And we can say then the length of the position vector at any time. Now before I just called that little r, now I'm emphasizing it's the magnitude of the position vector. Well, that would be the magnitude of big R t squared. And I'm not going to prove this right now. You could show this by looking at the components or writing it out explicitly, but does it seem plausible that we can pull the t squared out since it's just a number? This would really be t squared times the magnitude of r. I just pulled the t squared out. Again, if you want to use Pythagorean theorem to check that this works, go ahead. But so that means we can, let's just find the magnitude of r, which doesn't change. At all times, big R is just, by definition, 5, 4. And big R, well, that's the square root of 5 squared plus 4 squared. I'll write that as raising to the 1/2 power. We've already found that, right? Isn't that the 6.40? So there it is. The magnitude of the position vector at any time is t squared times the magnitude of r, which is about 6.40 t squared. That might have been a more direct way even of solving part A. What's going on in part B? They'd like us to find an expression for the particle's velocity as a function of time. So in part B, velocity as a function of time equals what? Let's do this a couple ways. One of the previous presentations looked in detail at why the velocity function is the time derivative of the position function. We've talked quite a bit about this already. The definition of velocity is the instantaneous rate of change of your position. This really says dr, or change in position over change in time. And something I emphasized in that previous video is that provided your vector is given in terms of its Cartesian components, all you have to do is take the derivatives of the components, and you've got your derivative vector. So that's going to be d dt of 5t squared I hat plus 4t squared j hat. And I've got these nested parentheses. Maybe I should have used brackets on the outside so it's a little easier to look at. Here's another way of writing it. So I'm writing or just to indicate an alternative notation. I could say d dt of, and then just write it this way, 5t squared comma 4t squared. And now we go ahead and differentiate each component. It's as simple as that. Provided that your components are Cartesian components, rectangular components. So that's going to be, well, this is trivial now, right? You guys know how to do this from first semester calculus. You bring down the 2, this becomes a 10t, and this becomes 8t. And now if I'd like, I can pull the t out and write this as 10, 8, all of that times t. And that's really the answer to the question that was posed in part B. Find an expression for the particle's velocity. So they didn't say speed, they said velocity, which is a vector. We now have that vector. Here's another way of doing it. Let me use this capital R vector that I introduced. I can say since the position vector as a function of time is this constant vector r times t squared. Now, once again, here's a result that I'm not going to prove right now, but it should seem plausible to you. If I want to take the derivative of the position vector, since this is a constant, I can just move my derivative right past it. It doesn't affect the constant. It's kind of like in calculus. Remember the derivative with respect to x of some constant times f of x. We just pull that constant out front and say that's the constant times df dx. That's what we're doing here, but our constant in this case is a vector. So this is really big R times d dt of t squared. Just move the derivative right past the constant vector. The time derivative of t squared, of course, is 2t, and so we end up with 2t r, and that's a perfectly valid way to write it since we've already specified what r is. Where's that? It's this 5 comma 4. Well, just to check that this is consistent with this, because these are two different methods for getting the same answer, let's go ahead and multiply 2 by our vector big R, which is 5 comma 4. So that's going to end up being 2 times 5 comma 4 would be 10 comma 8. Don't forget the t. It doesn't matter if you write the t on the left or the right. So yes, same answer. It's up to you to decide which you like better. Lastly, part C. Now that we know how the vector velocity depends on time, they would like us to calculate the speed at a number of times. In fact, the same 3 times as part A. They'd like us to find the speed at 0, 2, and 5. Well, remember the relation between speed and velocity. If you get pulled over for speeding by a law enforcement officer and they ask you, do you have any idea how fast you were going, you don't give your velocity, right? You don't say, well, the magnitude of my velocity was probably 64 miles per hour, but my x component was negative such and such. Speed, which we write in this class as just the letter v. No vector symbol, no arrow. V in this class means the length of the velocity vector, the magnitude, which we can find using Pythagorean theorem. You can do that with any vector, right? Add the rectangular components in quadrature to find the length of the vector. So let's do that. Because we've already got our velocity vector right here. Remember, this t gets distributed to both. Now, let's try this. Yeah, I'm going to stick with this way of writing it because the absolute value of the velocity vector, again, this means the same as that. Well, I've already written that here. That would be the absolute value of 2tr. And I chose to do it this way because now it's very easy to recognize. I can just pull the 2t out and take the absolute value of big R, which we've already calculated. This way I don't have to mess with using Pythagorean theorem and squaring the two components, both of which have a t in them. I'll go back and do it that way too, just to show you that it works. But we've already found that the magnitude of R was 6.40, so what is that, 12.8 after you multiply by 2? 12.8 t. That's a little sloppy, sorry. 12.8, that's too bad. 12.8. It's not any better. I'm having trouble with my 8s here. This is embarrassing. There we go. You do, so much more typing these days than writing. My handwriting has suffered. Let's confirm this result. I suppose before I do that, how about we evaluate it at a particular time? We'll do the same time that we did in part A, which was t equals 2 seconds. So the speed at 2 seconds, pardon me. So this is a short way of, This is a short way of saying evaluate the speed at time 2 seconds. I just plug the number 2 into t. 12 times 2 is 24 plus 1.6, so I think that's going to be 25.6 seconds. And let's check that with the solutions manual. They round it to 26. All right. And we might as well do this the slightly more cumbersome way. another way to calculate the speed, or the function for speed, would be speed is equal to the square root of the, and how about I do it this way? I'll emphasize that we're squaring both components of velocity, adding them up, and then taking the square root. What are the components of the velocity? We found previously that they were 10t and 8t. So that's going to be the square root, and you know what? Let me do it this way. I'll put everything in brackets. That's going to be 10t squared plus 8t squared, all of that to the square root. And again, here we can factor out a t squared. I've got 10 squared plus 8 squared. See how it's kind of unnecessary to do this? We see where this is heading. I've factored out the t squared. Once I take the square root of t squared, I'm back to just t. And now we've got the square root of 10 squared plus 8 squared. That's 164. What is the square root of 164? 12.8. So of course it came out the same. That's supposed to be a 1 there. 12.8 times t. Same expression that we got using this device of a capital R. So you do it however you like. Maybe you should do it a couple ways. That'll help you learn. Number 40 from chapter 3 is a little more fun as far as homework problems go. I'm not saying it's a rollicking good time. Let's read through the problem here. You've got a treasure map, how old-fashioned, and the instructions say, start at the ye old oak tree, walk due north for 500 paces. That's a pretty imprecise unit, right? It's not a meter, it's not a foot. Everybody's pace is a little different than the next person's. Then due east for 100 paces. So 500 north, 100 east, dig. The problem is, evidently there's a dragon in the way, on the way to the tree. Of course there's a dragon, and to avoid the dragon, you have to go around. So first you start off by going down the proverbial yellow brick road by only 300 paces. That ought to be enough to get some clearance around this dragon. And then we want to hook a left back towards the treasure. And rather than just go willy-nilly and guess at which direction, we're supposed to figure out, after you've gone 300 paces along the yellow brick road, which is, by the way, 60 degrees clockwise from north, we're supposed to figure out which direction to face and then how far to walk to get to where X marks the spot. Now this is chapter 3, which is about vectors, so hint, hint, this is going to be a problem with vector manipulation. So here's our map, magnified. Remember, we're supposed to start at ye old oak tree, and we'd like to wind up here. So that net displacement from tree to treasure could be labeled with the vector that I will call vector A. And you'll recall that the statement of the problem does not tell you what that vector is in polar coordinates. They don't say, walk a given number of paces at a particular angle. They give you the steps that you need to walk north and east. And you'll notice that if we have an XY coordinate system superimposed on this picture, that would correspond to the rectangular components of this vector. So just to remind you, 500 paces north, 100 paces east. And so I've indicated the rectangular components of my overall displacement vector from tree to treasure. And those components are given. So the X component would be that final 100 paces east. I'll call that a positive 100 if I've got my normal coordinate system where the X-axis points that way and the Y-axis points that way. So that would make the Y component of our vector a positive 500 paces. Great. So we know the rectangular components of the desired overall displacement. Now, what are we supposed to do with that information? Are we going to turn that into polar components? Is that even necessary? Well, remember, that stupid dragon's in the way. Does it look scary? Scary enough? Yeah, I guess we better go around that thing. Whoa, what is happening here? I didn't know PowerPoint could do that. That was cool. So instead we set off down the yellow brick road. I almost want to sing the song. 60 degrees east of north, that's the direction of the road. See how that angle is indicated here? Vector B, which is our displacement down the road, is at an angle 60 degrees clockwise from the vertical, or you could say 60 degrees east of due north. So not only do we know the direction of vector B, we also know the length of that vector, because we're told that we're supposed to, or we start out by walking 300 paces down the yellow brick road. So if you think about it, we actually do know everything about vector B. We know its polar components, the length of the vector and the angle it makes with the vertical in this case. So they didn't give us theta B measured with respect to the x-axis. They gave it to us measured with respect to the vertical, which corresponds to the y-axis. And what they're asking for, what we're supposed to find here is once we've walked our 300 paces down the yellow brick road, which way do we turn, which I've specified with this angle phi. So I'm going to solve for phi, which is the angle that we should face with respect to due north, and we need to figure out how far we walk from the brick road to the treasure. So I'm obviously labeling this vector c, and right here, instead of writing c with the arrow symbol, which means c the vector, I just put c, which indicates the length of the vector. That's really what we're looking for. How far do we walk after leaving the yellow brick road, and in which direction? So we're solving for the length of that vector and that angle, which I've called phi, fo, fum. Well, the great insight here that will get you started, this is really the only thing you have to realize, and then the rest kind of takes care of itself. As long as you know how to manipulate vectors and to convert between the rectangular and polar components, you're good. Anytime you see a triangle composed of three vectors, you should immediately recognize, hey, I can turn that into an equation. I can either write it as the addition of two vectors or the difference of two vectors. In this case, we've got vector B and C drawn tip to tail. So a displacement down the road plus the appropriate displacement away from the road should equal the net desired displacement from tree to treasure. Which of these vectors do we need to solve for? Well, we already know vector A. We know its Cartesian components. We know the polar components of B. We're looking for vector C. We would like to determine everything that one can determine about the vector C. So if you solve the addition equation, right, all I did was translate this picture into an equation. B and C, tip to tail, make vector A. Let's solve this top equation for C, and I get this equation. All we have to do is take the difference of vectors A and B, and we will know what vector C is, the displacement C. Well, from the previous video, we should understand now that this is really, in the plane, this is a short way of writing two equations. It's true in the x direction, and it's true in the y direction. So if one vector is the difference of two other vectors, then the x component of that vector is the difference of the x components, etc. Simple as that. So do we know these four components? See how there are four components here? X and y for vector A and x and y for vector B. Well, we definitely know the x and y components for vector A. Those were stated in the problem. We need to find the rectangular components of vector C. What we know is the length of vector B and the angle it makes. Let's turn those into b sub x, b sub y. Then we will be ready to evaluate the right side of these equations. Once we have the rectangular components of C using this prescription, then we can complete this picture here. We'll know the y component of C, the x component of C, and we can turn that into a magnitude and an angle. See how we're just going back and forth here? Cartesian components to polar components, vice versa, and we're adding or subtracting components of one vector to get the component of a third. That's really all that's going on here. Excuse me. So I've resolved vector B into its y and x components, and let's use a little trigonometry to solve for those components. So let's see, the side here, the picture's a little muddled. This 60 degrees, that's the angle in this corner here. So this side of the triangle, which is the x component of vector B, that side is the side opposite the angle that we're given. That's 60 degrees. So if I want this opposite side, I should take the hypotenuse and multiply by the sine of 60 to get the x component of B. And that's what I've done here. Hypotenuse times the sine of 60 gives us the opposite side, which is b sub x. Now, do you notice how It wasn't necessary to insert a minus sign because if I look at this triangle or this vector, I can see that the x component of b points to the right. That's a positive component. No need for a minus sign. All right. This is basically 260 paces. Does that seem reasonable? Well, remember, the overall displacement down the brick road was 300, and this is the larger component, so 260 does seem reasonable. How do we get the y component of displacement b down the brick road? Well, this side of the triangle is adjacent as far as this corner angle is concerned. So we take the hypotenuse, we multiply by the cosine of 60 to get the adjacent side. Again, because that component, whoops, I've got an extraneous vector here. Because that component points upwards, we know it should be a positive number. No need to put a minus sign out front. And observe how the trig functions that I'm using here are different from the conventional formulas. If you always use the angle with respect to the positive x-axis, then you would say bx equals hypotenuse times cosine of theta b, and then for the y component you would use the sine of theta b. The reason these functions are different is because we're not using the conventional angle. I'm using a different triangle here. So again, be flexible with your trigonometry. This comes out to be a nice whole number. You can see that because I think this is worth memorizing. The cosine of 60 equals the sine of 30, right? 60 plus 30 equals 90. Cosine of 60 equals the sine of 30, and I know that the sine of 30 is 1/2. Half of 300 gives us that 150 paces. Okay, so now, does that mean that you're actually going to walk 150 paces north and then 260 paces east? No, there's no need for that. Just take the 300 paces directly down the brick road as stated in the problem. And now it looks like we know bx, by, ax, ay. We can evaluate these formulas down here and find the Cartesian components of our final displacement. So plug in the numbers. Here's what I get for c sub x, and appropriately, it is a negative number because obviously we're going to have to go to the left in order to get back to x marks the spot. And for the y component, plug in your numbers. Evidently, we need to walk 350 paces north and negative 160 paces, basically, or I should say positive 160 paces to the left. Now, are you actually going to do that? The way the problem is written, it's kind of assumed that you're going to take a straight line path from the brick road to the treasure. You could actually do the Cartesian displacements like that, but why waste time? I'm sure you're anxious to get to this treasure, whatever it is. Now you got me thinking here, what would I want that treasure to be? Gold bricks? Unobtainium? I don't know, a bunch of N95 masks? It's fun to think about. Okay, let's turn those Cartesian components back into polar components. So I've redrawn vector c with the magnitudes. Notice I didn't put a minus sign here. Yes, technically this component is a negative number, but I'm just indicating the absolute values, meaning the lengths of the sides of the triangle. A triangle can't have a side with a negative length, right? That doesn't make any sense. And here's where, rather than rely on any particular formula, let's just use our understanding of Pythagorean theorem and the trig functions. So we're interested in knowing the overall number of paces we need to walk in the appropriate direction. That would be the hypotenuse of this triangle. So we use the Pythagorean theorem to find 385 paces ought to do it. And I rounded to the nearest integer. There's no sense in keeping a bunch of decimal places because remember how imprecise this is anyway? All of the displacements are specified in paces. That's not an SI unit. So honestly, this probably wouldn't work out very well, would it? Because even for a single person or an individual, your paces aren't regular. So you're going to get to where X marks the spot. You'll start digging and you probably won't find anything. You're going to have to dig a really big hole with a large radius before you finally discover whatever it is you're uncovering. Unless it's like a giant alien saucer spaceship that got buried underneath the snow millions of years ago, like in that movie The Thing. If it was that big, then I suppose you'd probably have success on your first insertion of the shovel. Last thing here would be to find this angle. You'll notice that as far as this angle is concerned, this is the opposite side, this is the adjacent side. When you hear opposite and adjacent, you should immediately think of the tangent function. So if we take the arc tangent of this over this, that will give us the angle. Remember, if you plug a number into the tangent function, what you're plugging in is an angle. We don't know the angle, we want the angle. So an angle is what comes out of the arc tangent or inverse tangent function. You plug an angle into tangent, you get an angle out of inverse tangent. We want the angle, so let's use the inverse tangent function. And am I going to cover the screen with a big warning to check your quadrant? Not in this instance, because we're using a triangle where the interior angle is less than 90. So we know we're in quadrant 1. Again, yes, this vector technically points into quadrant 2. If this is quadrant 1 and this is quadrant 2, yeah, the vector points into quadrant 2. But I'm talking about the angle, this interior angle here. That angle is a quadrant 1 angle. So we don't need to worry about checking our quadrant when we take the inverse tangent. So on my calculator, I would evaluate the ratio first, do the division, hit equals, then take the arc tangent, and I find 24.5 degrees. Your solutions manual rounded that to 25 degrees. But you know what? When you're walking a long distance, like 385 paces, even a small error in your direction will put you way off course eventually. So you do want to be precise with the angle, and that's why I kept it as 24.5 instead of rounding to 25. If you start off half a degree in the wrong direction, you know, a mile later, you're way off. And there's our answer. Once you've walked your 300 paces down the yellow brick road, turn and face, as I would put it, 24.5 degrees west of north. See that? If you're facing north, you'd have to turn towards the west. So we say 24.5 degrees west of north. That's your bearing or heading. Is it heading or bearing? I forget. And then you walk 385 paces. That should put you at the treasure, and you've successfully circumnavigated the dragon there. Of course, on the way back, I guess you could just retrace your steps. I'm a little disappointed that there's no actual treasure at the end of this problem, except for understanding.